Hello, and thank you for joining us. Welcome to this webinar event. This is one of many such webinar-based professional development events brought to you by Texas Instruments Australia as part of our ongoing support for teachers in the classroom. Today's topic, graphing and using functions on your TI-nspire. Your presenters are Roger Wanda and Sanjeev Meston. Good evening, gentlemen.
Good evening.
My name is Brian Lannon. I'm your host for this evening's session. I have had the honour of hosting many of our webinar events, and I certainly enjoy doing that. It gives me the opportunity to interact with some great presenters here and teachers from around the country, and see what they're up to. Sanjeev Meston is internationally experienced. I've seen him presenting sessions, in fact, in the USA. He's a mathematics and physics teacher of some 33 years' experience, and you can see he has a particular interest in STEM and also the senior subjects, VCE, the International Baccalaureate, also HSC, and foreign curriculums, so both UK and Indian curriculum-based. He is currently heading the mathematics faculty at Flinders Christian Community College. Thank you for joining us, Sanjeev.
Thank you, Brian.
And our other presenter, Roger Wanda. He's been teaching in Victoria, South Australia, USA, 3 decades experience, and also lecturing in education at the Melbourne Graduate School of Education, which is part of the University of Melbourne, facilitating professional development sessions for teachers. And he particularly has an interest in the use of technology in the classroom, as well as teachers' statistical literacy. Good evening, Roger. Thank you for joining us.
Good evening, Brian. Good evening, everyone.
I'm going to stop sharing my screen and hand this over to Roger.
Well,
and
thank
Roger,
you, Brian.
Sent me some files, yeah?
I did, yes. And so I will share those here, and we're going to be looking at an overview of what I've written for this first. So good evening, everyone. During my portion of the segment tonight, I'm taking a look at polynomial, exponential, and logarithmic functions. And I'll just give you an overall idea of the problems in the structure. Each of these have been written for the webinar, and I'm hoping to illustrate some of the advantages of defining functions, and these are functions that are used by maths method students. The areas of study that are included in these 3 activities are listed there, and I feel that with a bit of tweaking, as teachers really should be doing with anything, that these activities could form the basis of an in-class investigation, or if you have some school-assessed coursework, a task that you want them to do, and possibly choose different functions, and et cetera, but along the same lines, they could form the basis of that. So I'm hoping that they prove useful for teachers of mathematical methods in particular, but in function work in year 11 and 12. So the first one deals with polynomial functions, and we're going to take a look at this problem where we have a quadratic and a linear function, and we're going to take a look at the minimum distance between these 4 key points, the 3 intercepts and the turning point of the quadratic function graph to the linear graph, and then to use the both the algebraic functions and also the graphical functions to illustrate what you've actually found. So now keep in mind that you will receive all of these files, and I've taken the screenshot from this and the other 3 activities and put them in a notes page on the first page of the nspire files. So and that's very easily done. So one of the beauties of the notes page is you can pretty much put any kind of a problem on there. The file that I'm working from, a TNS file, that's the code for it, and this .tns file, and the other two are also going to be available on the TI website. It consists of 3 pages, a notes page, calculator page, and a graphs page, and the contents of those are illustrated. Because we have a very short amount of time here, so you're bound not to remember too much at first glance, but when you come back to it, that'll serve as your little reminder. The big thing here for defining functions is that you find that most easily, if you're advising your students for this, to go in the calculator menu, to go to actions, and the first one up there is define, and then the words D-E-F-I-N-E is right there. If you're using a computer, then typing it in is probably just as fast. Activity 2 will deal with exponential functions, and this is the situation here where we have an exponential function meeting up with a what we might call the inverse square function, having a point of intersection, and then taking a look at the area enclosed between the y-axis and that point P, and seeing if you can find where you would have that same area replicated to the right of point P. Then in activity 2, once again, it's a 3-page Inspire file with a notes, a calculator, and a graphs page with the main things that are being done on each of them listed there for you. Finally, activity 3, dealing with a logarithmic function, a point P, which is the x-intercept of the function, and point Q, having a first coordinate that is twice the x-intercept, and using some storage of function values there to help you along, and some sliders you'll notice on the graph. So that file is a 4-page file with a notes, a calculator, then another notes page, and finally a graphs page. We'll be going back and forth on there. So we'll see how we go. I'll be conscious of the time and handing over to Sanjeev at 7:30. So just a final reminder there that if you want to contact me later, there's my email address, and I'm very happy to enter into some email discussions with you as we go along. So that ends the slide component of that, and I'll just go over to my Inspire file, and we'll take a look at that and start off on that. Now, this is the Inspire file for Activity 1. I'll just mention here that Activity 1 actually has, if I take a look at Control Up, it's actually got 2 problems. The first problem is all the working out that I did to develop the problem. It's got the complete algebra there. In case I do what usually happens, which is running out of time. Problem 2, we're going to try to at least start the creation of that problem, and then we might just depending on what the time is, because I see it's already 7:10. So we'll take a look at the start of problem 2, which is the page. And again, all I've done on this notes page is put a screenshot from the PowerPoint on here. So we've got our functions f of x is the first one, and we'll be taking that linear equation that you can see here and rejigging that as a g of x and putting that on the graph. So here we go. On page 2.2, I've decided to insert a comment here, and this is a really good thing, I think, for teachers if they want to send a file to students and students are going to get interrupted, teachers are going to get interrupted. It's just a little reminder comment about what's going to be done. Now, it doesn't have the word processor powers of a word processor, and it doesn't have the capabilities of changing the fonts, etc., that you do on a notes page. But insert comment is a really good thing on a calculator page to keep a focus on what's actually going on. So we're going to define f of x. So I'm going to start off with that with define, and as I said on the handheld, if we go to menu, actions, define is the first value here, and we're going to define f of x to be equal to the function brackets, x minus 2, close brackets, squared, minus 1, enter that. And I've just taken the opportunity to rejig that linear function, x plus 2y equals 10, to define that as g of x. So this is just to save a little bit of time here. So once again, we're going to define, and you notice that I just typed it in here, which as a teacher we can do really easily on the laptop. It's easier for more students to use the menu actions define that way. But define g of x, and that'll be defined as negative 1/2, and I'm going to try to use best practice here to set up the fraction template, negative 1 as the numerator, down to 2, so there's negative 1/2 times x, or just x, that'll be fine, and then plus 5. So we've got f of x and g of x. Let's take a look on page 2.3, which I've already set up as a graphs page for us, just to save a little bit of time. f1 of x, we'll say that that's our original f of x, and see, this is the beauty of having it defined, so we don't have to enter the equation in there. We've got that equation. We're going to be using it later on in the algebra back on the previous page. So here's f of x equals, f1 of x equals f of x, so our quadratic. And then we'll get a second entry line going up there for f2 of x. We'll put that in as g of x. And so there's our linear and our quadratic functions. And after doing that, let's go back to our page 2.2, and where it says, then we're going to actually be letting, in this comment, we're going to let the point a f of a represent any point on f of x, and we're going to be using a slider. And what points are they going to be? Well, they're going to be for the points capital A, B, C, and D that are there, which conveniently for this one have x coordinates of 0, 1, 2, and 3. I hope you can see from that graph. We're going to, if f of a represents any of those points along f of x, then a second function, a third function, h of x, is going to be defined. So define h of x equal to, and that's going to be 2x minus 2a plus f of a. Now, in case you're wondering where I've got that from, that's just taking the y minus y1 equals m brackets x minus x1, using the fact that since the linear function has a gradient of negative 1/2, the distance, shortest distance to the graph is always going to be the vertical or the perpendicular distance, so that will have a gradient of 2, so that shows up here. And so I've just taken that fraction and rejigged it, instead of calling it y, I'm calling it h of x. And so I've got that graph where I've got that function there. Now, in this one, if I go to my entry line and put in h of x, I'm going to put it in, and it's going to say, well, you want a slider, don't you? And I say, yes, of course. And I'm going to use the variable a, so we'll say that. And we'll start that off. If I want to check the settings of that slider, I'm just going to go up here and just make sure I've got the variable a. I'm going to change the value to 0 because I want that to start off at that y-intercept. We'll let the minimum be -5, maximum be +5, and we'll have that going up automatically. At this stage, I'm going to have it be a horizontal slider, and I'm going to have it minimized so it doesn't take up so much real estate on the screen. And what you can see there is that I've now got my graph that's going through the y-intercept. If I change the slider to a equals 1, then it's now going through the first x-intercept. Go to a equals 2, it's going through the turning point, and a equals 3, we'll have it go through the second x-intercept. Now, because it's already 717 and I want to get into the other files, I will just show you briefly what, if we had more time, we would be doing. There's a lot more algebra to be done on this after the after this. I'm going to go to the file that that old phrase, is something that I prepared earlier. But this is what I prepared earlier with h of x, and create a distance function so that you can use calculus on this distance function if you wish. It's going to be defined in terms of a. Remember, a is the point that's related to it on the parabola. But of course, once you change the value of a, then you change the calculus involved, etc., and that can just confirm the measuring that you do when you use the measuring of the distance between that point. Say if it was back up here at, I just changed that to 0. I'll go over here, change that, and go to the left. But that distance is already measured by using the measurement function of the line segment between these 2 points. There's a lot more in this file, but it just gives you an idea of what you can do linking the sliders and the defined functions. I'm going to dash over because it's now almost 7:20, and take a look at this next one, which is taking a look at an exponential function, and it's going to be intersecting with that inverse square function. Once again, we're going to take a look at page 2.2, where we're going to define the functions first. So once again, I'm going to define f of x to be equal to, here's e, and it's going to be 2 times e, so the function is 2e to the power of negative x. This might be different to what I had up on the screen before. And then plus 2 into that, and we'll define g of x equal to the square root, control x squared, x plus 1. Now I want to have plus 1 outside the brackets, and this is where students and teachers can get caught. The cursor is currently underneath the square root sign. Go 1 step to the right, and you're suddenly outside the square root sign. It's very important to be able to do that. Enter. And let's have a look at what those graphs look like here. So I'm going to go to page 2.3. Once again, it's inviting me to do a sketch graph, so let's have this be f of x. And a slider for E. Now, why is that happening? No, I don't want that to happen, so I better go back here and just check what I've got here. 2 times e to the negative x, f of x. No. Line.
I can see it's definitely Euler's E that you've got in there.
It certainly is.
Yep.
I clicked down here. That's right. Yes, and you have to. So Not sure why that's happened, but I'm going to, because of the time, I'm going to look now at the functions that we have up here listed, and just take a look at what actually happens with this, because we have some other functions that are defined and some calculus involved. You notice that we find the point of intersection. It's going to, of the two graphs, f of x and g of x, they will intersect at x equals 1.33 approximately. The x value, the y value for that point is found, and then that x value is stored, and the store value, the store function is with control, and then this, control variable for storing, and that becomes very useful when we set up the integral. I'm now going to dash over, as it's 7:23, I'm going to dash over to activity 3 and take a look at this function, which deals with a logarithmic function where we have y equals a times the ln of x plus b, and once again we're going to have a couple of sliders. So on page 2.2, which is a calculator page, once again let's define, I'm going to call it g of x, and there's a reason for doing that, so we didn't, because I introduced the letter k, and sometimes f of k becomes controversial in some classrooms, so better to leave that off. So g of x is equal to a times, we better make sure that we do that, the ln, natural log, of x plus b. Enter that. And in page 2.3, set up a notes page, and I've got it set up. First of all, we're going to be putting some sliders in, and those sliders can they don't get put into a math box. They just get put in this space here. So I'm going to right click, which remember on the handheld is Control Menu, and insert. Whoops, we want to insert a slider. Escape. Actions. Escape. Maybe I do have to insert a math box here. That's and if I insert a math box in here, then whoops. And you insert slider. Now I followed the wrong one, so get that out of here and go to Menu. Insert slider. Here we go. Here we go. And the variable that I want first of all is the variable a. I want that between -1 and +1. I'm going to have it start off with the value of 1, and I'll make that going up by 0.1, 0.1. I'll make it horizontal, and I will make it minimized as well. And I'm now going to have a second math function where I insert another slider, and this one is going to be for the value b. Same deal. Have it start at 1, go from -5 to +5, have the value that it's going up by 0.1. Whoops, not 0.1, but 0.1. I want it horizontal, and I want it minimized. Okay, those will become useful later. Now, at this stage, because I've got A and B defined, it means that on my graph stage, 2.4, I can actually see what the function f of x looks like, or g of x. G of x is the function that I had defined, because remember that I had my sliders for g of x. Now, if I want those on the screen here as well, and I think that would be a good idea, I want to go to Menu, Actions, and insert a slider once again. And it's going to be the same slider with the same conditions, 0.1. Minimized, have that on the screen as well. And it usually plunks it where you don't want it, so I'm going to put it over here. And then once more, I'm going to put another slider, just so I've got a little bit more control. I'm going to need the sliders twice. Menu Actions, insert slider. We're going to make that B. And do the same things that we've done before. 0.1, and minimize that. Okay, and once again, that's over here. Oops, grab, oops, not that label. Grab the slider, and move it over to there where it's nicely out of the way. And we can see that by changing the values of A as we're going along, and remember that A and B were the variables in the function, and if you've forgotten by this stage what the function was, there it is, A times the ln of x plus B. And as I make my changes to that slider, the sliders also have changed in the window, so it's all connected, which is really nice because we've used the same variables A and B. Okay, the next thing I want to do on here is I'm going to change the window zoom. I'm going to zoom in a little bit so that I've got that blown up a little bit. And there we go. We've got a little bit more definition there. Escape from that zooming and then bring that out a bit so that I've got my settings for my window a little bit more defined. At this stage, I want the x-intercept, so I'm going to go to Menu, Geometry, Points and Lines, and find the intersection point between the x-axis and the graph. And there it is. It's zero. Looks like it's at about 0.2, right there, or close enough to it. I'm going to look for the get out of that menu by pressing Escape. Going to get out of that menu. I've done that. I want to go to the point and go for coordinates and equations. And at this stage, I can see that the actual coordinate there is 0.174. At this stage, I'm going to highlight the 0.174, and I'm going to store that as the variable h. Press Enter. And that's going to be important because the next thing I'm going to do is put a point on the graph, and I'm going to make, go back to my calculator page, and I'm going to I'm going to say that 2h is going to be stored, control variable store, as the letter K. And you can see 3.4 approximately. Okay, so that's double what the x-intercept was at the present. So remember, it's all linked. At this stage, I'm going to go to my Escape. I'm going to go to my menu, Geometry, Points and Lines, and I'm going to put another point on the graph. I want to put the point on here. It just puts it any place. Escape. But what I want to do now is link that variable. I'm going to take that variable and I'm going to link it to the variable k. And so you can see now that no matter what I change a and b to, as I change a and make that bigger or smaller, I've got the conditions set out in the problem where the coordinate of this point, which you can later label as q, is going to be that should be twice the value. That's not twice the value there, though, is it? So okay. Well, something else must have changed here. I'm not sure exactly what that was, but I can see that once again, if we go over to the page where I did have that before all linked up and do the changing, P and Q are there. And in terms of changing that coordinate, that will change as well. Okay, well, at this stage, I'm going to say thanks very much to everyone for listening. I'm going to be handing over now to Brian, who's going to take you over to Sanjeev, and I'll look forward to hearing what Sanjeev has to say about 3 other functions. So thank you very much, everyone. And we'll go now to Brian, who's got the screen again. Thanks, Brian.
Yeah, thanks there, Roger. And I've just handed the ball across to Sanjeev, so we'll wait for him to screen share. In the meantime, you're seeing the background PowerPoint that we were playing at the commencement of the webinar. I think there's some questions coming in there, particularly about the sliders. The insert slider from the menu is something that works across a range of application types. The other way to do it is, and we saw it happen there, when you define a function, for example, you've got f1 of x, that means the first function that's being defined in terms of x. If you're doing that on a graphing page, for example, you define f1 of x equals, well, a classic I like is ax squared plus bx plus c, okay, the general form for a parabola. As soon as you press enter, you will be prompted because the a, the b, the c are not yet defined. You will be prompted to create sliders for those 3 things. Try it. Just take your handheld, go to a graphing page, start a new problem, new graph, and just define f1 of x equals ax squared plus bx plus c, and it will automatically set up the sliders with a reasonable range of values for those a, b, and c. And of course, that's a standard exercise that we do with students about year 9 level, seeing what happens as we adjust those 2 coefficients in the independent term. So great stuff there. Yeah, thanks again, Roger. Sanjeev, we're seeing your smiling face on screen now.
Thank you, Brian. And I'll get started right away. Okay, Roger has already spoken about defining the function. I'll quickly show you a few other ways in which we can define the function. I personally use the graphing screen more often. That's my preferred way, but everybody has their own way. Then, of course, Roger has shown you the define option. We can also do the store or assign option, and then we can actually enter the function on the calculator page and go into math actions, and that gives you the option to define as well. So I won't go through all this. I'll just display the screen captures that I have over here. So you will see that's defining it on the calculator page. I've defined the function as h of x. Now, I just want to show you something here quickly. That's my calculator page there. I actually will insert a graph page, and I can actually call the graph anything. I don't have to call it F3. I can call it, if I'm talking about square root function, I can call it SQ, or I can actually enter a word over there, and then I can just go and define my function using the template. So that's one way of doing that. So I've got a screen capture there for that. So I could call the function anything. And once you have defined it, we are just testing. I define the function as h. Now you can see h. If I do h of 2 and x is 2, it gives me the value. It gives me the value there. Because I had actually got a domain, if I go back, you will see I actually put a domain there while defining the function. I said x lies between -3 and 6. And when I'm trying to find h of 5, obviously it's going to be a -5. It's going to be undefined. If I just type in h of x, it gives me the actual function that I had stored. Now, most of you will realize that we do have a feature in the calculator, which is domain. You just type the word domain or get it from the book menu, the catalog. If you type in the letter D and go down to domain, the only thing you have to put the function and then go comma x. If you forget comma x, it's not going to work. So it gives me the domain for this function. I can find the function maximum as I've done over here. I can determine the function minimum. So all by defining the function. Now the next option I've done over here is the assign option. So control and then this key over here. You can see that blue symbol over there for assign. So I'm saying assign x squared minus 5x to gx. So that's another way of defining the function which I've done there. And it works exactly the same way. So what I did on the previous screen, now I've done using the assign option. And then the last option that I'm going to show you is the store options, which is here. So control and the variable key. And on top of that, you'll see store. So control and variable will actually store it. And that's what I've done. So I've stored x squared minus 5x plus 7. That's the store symbol. And I've stored it as a function p of x. And exactly what I did in the previous screen. So a few different ways of storing a function. And I have grabbed it over there. Now you will see there's another option here. I've typed the function which is qx over here, which is a quadratic. And when I do actually right click, which is control menu, it goes into the option of math actions. It says define function. And if I click define, it will actually define the function. And then again, I've just done a test for completing the square for my define function. And that's just a smart way of putting, I just put y in front. So those are a few different ways of defining the function. I'll move on to sketching the graph for an inverse of a function. And obviously to get the inverse, we know it has to be 1-to-1. If it is many-to-1, we'll have to restrict the domain. But I'll first show the basic shape how we can get the inverse. So I've gone into the option and we'll graph a function here. So I've grabbed the function x cubed. So I can see my red graph is the x cubed graph. And now I'm going to actually jump to my calculator and show you there. So Control G is a shortcut to go into the edit or the function menu. Now if I click there, it gives me various options. I can graph a function and I'm going to do x cubed. So I've got my function. It graphs it beautifully there. If I want, I can change the color. I'll quickly show that. So that's the color, the line color. I can select any color. If I want, I can make it go bold by selecting the attributes. And I've made it go bold. Now, I've already defined my function. If I want to actually do the inverse of this, once again, I'll do Control G here. And this time, I'm going to use the option called relation. And here, I'm going to do f equals. Now, I've already defined the function as f3, so I'm going to use f3, and you'll see it goes bold. So it tells me that I've already defined something. Now, instead of x, I'm going to actually put y now. So we have just swapped those positions of x and y. And this gives me the graph for the inverse. So that's a quick way of doing the inverse function. So that's the graph we had. And now Roger actually already showed you how to store the values from the graph. So I actually won't go through that bit. So we do have a graph. So if I use the store option, I can store those values. Now what I've done over here is actually plot the inverse using the screen capture value, and I'll quickly demonstrate that. So if I go back to my calculator here, I insert a list and a spreadsheet page, and let's call this as X value, and this one here is Y value. And if I click here, and if I go into menu, it gives me the option for data capture, and I'm going to use the automatic option, and it says put a variable. So I need to actually go back there first. I need to define a point, store a point. So geometry, point on, and let's put a point on the actual function. Roger showed this bit, so I'm going to store that as x1. And I'll do the same there, store that as y1. Now if I go to the list and spreadsheet option, all I need to do is put x1 there, and that's 1, and if I click enter, it puts the current value over there, and my calculator is set to exact, so I'll just go and change my settings quickly. So I'll change it to automatic, so that's better. And I do the same over here, data and data capture, automatic, and this time I'm going to put y1 there, enter. I'll just actually do a clear data. Now I'm ready. Now I don't have any values here, but now if I move this point here, it's actually capturing all these points where my cursor has just moved and it picked up. And you'll see the table actually has got populated there. All right. Now, if I insert another graph page this time, and I go into scatter plot, and now I want to swap values. So on the x-axis, I want to actually put the y values. You'll see it goes bold, and that's x values. And you'll see actually it gives me the inverse graph over there. Oh, sorry, I actually made a mistake. It captured the actual graph. I should have put it on x value and the y value on the inverse. So let's, anyway, the PowerPoint will demonstrate that. The idea is there. So that's just showing how to get the, so that's what I've exactly done. So the green one is actually the inverse. So that's just showing how the screen capture is done. So that those are the various inverses that I have plotted. Okay, now if I show you, we can actually calculate the inverse on the calculator screen. And I'll go here to my next problem. So if I look at problem 3, here I've actually defined the rule for finding the inverse. So define the inverse function. That's the rule that I'm defining. So I've actually got a function which I've stored as fn function, but you could store it as w, which I've done over there. So that's my function. I'm saying store it as w, which is stored, and then I'm saying solve this function, where in w replace x with y. We are saying x equals y, and we are saying that equals x because the whole function should equal x, and then we are saying solve for y. And it actually gives you the inverse. So this is something very handy. If you define this, this will always give you the inverse. And we know that the inverse of an exponential function is a log function. But the other interesting thing this does is actually it works out the domain without my even asking for it. So every time it works out the inverse, it will give you the domain. So I can go and change that function to anything. Let's change that as 5x. Sorry, let's get rid of the 3. 5x, say minus 2. And I can change the vertical translation. All I do is go and click evaluate. It will update the function, and you'll see actually it determines the inverse. Now I can replace that with a quadratic. So if I go and put that as a quadratic, I'll just put x squared, and you'll see it works out the inverse. So it gives you y is negative root x or y is root x, and it actually looks at the domain when you do that. So that's a quick way of finding the inverse. Then Roger has been through defining the sliders a bit, so I won't go through that. But over here you will see I've defined a function q1, which is a quadratic ax squared minus bx plus c. And what we are doing here is controlling the inverse. So it's actually going to take care of the dilation, and m actually will automatically control the. So this red graph that you're seeing is part of a quadratic. Now if you see, if I make it 1, it will show you the right side of the quadratic. That's the left side of the quadratic. So you can see the turning point, and it's actually working out the inverse. So I've put this as m times x is greater than, so that's the domain that I have defined. And now I can actually change the values of c, which is the vertical translation. I can change the values of b, and you can see it. That's the dilation factor there. All I need to do is that. So that's the right side of the quadratic, and that's the left side. So we can actually define functions to do that. And that's the maths where I have, rather on the calculation screen. I can actually even use this relation. I had stored relation 1 with x and y. And now I can solve this for y, and that's what we have done over here, and it gives you the function. So I can work it out from there. So my PowerPoint is actually going to explain that bit. So that's the rule that we use to define. So there's some calculations there. Okay. So that's another way to find the inverse. Solve, and we swap. Okay, I want to now move on to the piecewise function. Actually, I'm rushing through everything because I have quite a bit, and we are limited in terms of time. So piecewise function, we actually have a template. So on the calculator screen, you'll see these two templates. So the first one is for a 2-row piecewise function, and this is for n number of rows. So by default, it will go to 3. You can change the value. You can have 4 rows and so on. So I've got 3 over there. So that's the template for piecewise function. And I've now defined the function fx, which is in 3 pieces. And for each one of them, I've specified the domain. So I've got a linear equation. I've got a quadratic and a log function there. And this is the graph I get for that. And actually, you can see there's a point of discontinuity over there. So that's the linear part, that's the quadratic, and that's the log function there. And we are actually going to do a test of continuity over here. So I can actually split that into 3 different colors, and I'll show you how I have done that. So that's just a better view. So if I want to do that, I've actually stored each of the rows as a separate function. So that was my linear. I stored that as function px. My quadratic in the domain, I stored that as qx, and then my log function, I've stored that as rx. And this time, I'm actually going to use this template where my cursor is. So I'm not using the piecewise template. I'm using this template, and I'm defining a new function vx, which has the 3 predefined functions. And I'll show you the advantage of this. I actually tend to use this more than the template, and I'll give you some logical reasons why that is my preference. And the first thing, now I can do that. The first part comes as function 1, and second part of the function, and that's the third row. So first row, second row, and third row, I can select each one of them and actually assign it a color. So let's go and have a look at that quickly. So here I am, that's my original one, but this is the one I have changed the color. Now, if I select that, I can actually select the color option and line color, and I can go and change the color. And once again, I've just made it bolder by using the attribute option so you get a better view. And we are actually going to look at that point of discontinuity soon. So let's go here. You will see I have actually stored that as fx as well as vx. Now I've defined a rule. Now CON is a rule for check of continuity. So in continuity, we want to see, number one, that the function is defined at x. Then the limit exists at x, and then we are saying the lower limit should equal the upper limit. So I've actually determined all these values. I've stored this as a rule, and when I click that, it says done, and we are going to actually test it. So that's the one. So continuity at 0. If I get all the values as same, it actually tells me this function is continuous, because the function is defined at 0, the value is -2, the limit of the function at 0 is -2, and the lower limit and the upper limit, that's the left hand and the right hand limit, are equal. So if I get all these values the same, it tells me that actually it's a continuous function. And if I check at 2, it says yes, the function is defined, but the limit is -2, and then here it says the lower limit is 2, the left hand, and the right hand limit is 3 log 2. Now these are not equal, so it clearly tells me that this is actually not a continuous function. I have actually defined another rule, which is a continuity test. And in defining this rule, here, so that's the one. So we are saying that the function value at x should equal the limit. That's the first test. And then we are saying the lower limit, the left-hand limit, should equal the upper or the right-hand limit. So these are the two tests that we are going to do. And when I do the continuity test at 0, it comes as true and true. If both of them are true, it clearly says that the function is continuous. Otherwise, like I'm testing at 2, it says that's false, both of them. The lower limit does not equal the upper limit, and so they show up as false. So if I go back to my point, which is here, you will see that's the first piece in the blue, the second piece I've got in pink, and that's the third piece. This is how the function displays. And you can see I'm finding the function value at 1, that's the piecewise, and it gives me all 3 values. Whereas with fx, it will only give me the value where it is found. So it doesn't, it goes to actually all the 3 rows of the piecewise function. So those are the few reasons I use this option. Sorry, I'm rushing through everything. Okay, so I've just done the continuity and the discontinuity test. So that's all on the PowerPoint. I'll go to the last bit, that is circular functions, and we're going to look at transformations. So the blue one is my base function, which is sine x. And I have defined it in the domain of 0 to 2 pi. So that's the blue one. And the red one, I have defined it with sliders, which is a times sine b. So b is going to be the dilation from y-axis, which also determines the period. C is the horizontal translation, d is the vertical translation. And you will see that the domain is likely to change when it's the horizontal translation. So I've done c plus 0 and c plus 2 pi. So that's the lower end of the domain, and that's the upper end. And I've called the function sine, S-I-N-A, because S-I-N is already predefined. So I've defined that. And if I go to my calculator screen now, which is here. So that's my calculator screen. Now, if I change the value of a, sorry, that's gone to the PowerPoint. Yeah. So here, if I change the value of a, let's first make b as, so that's the horizontal, the period, it's controlling the period. I can control the amplitude with a slider, and that's the horizontal translation. So this is the sine function, and I can do a vertical translation. So all the transformations can be actually depicted through these sliders that I have defined. And if I put C back to 0, and I make the vertical translation 0, so you can, and I can adjust the period. So that's 2 cycles there. So that's my original graph where only there's a dilation taken. So I can control any of these values there. And you can see the domain changing. If I go and type this function on my, so I've called it sin x. If I go and insert a notes page, and if I do a math box, and I do sin of x, it will actually show me what the domain is. And it's probably, I need to just once again adjust my settings. And if I go back and change it to exact, it gives you the form then. And yeah, it's not a very, but you can see it's got the domain there. So it's actually got this range value there for 0. If I now move the slider, I can actually see the value changing on the page. Sorry, I have to change the value of C. If I change C, you can see that actually updates live. So you can see a live update there. I've done exactly the same thing for a cos graph. So the blue graph is the base cos graph and the green is after transformations. But on this particular page, you'll see I've actually inserted the sliders at the bottom, A, B, C, and D, instead of separate pages. So that's a notes page. And I can actually control the sliders from here this time. Instead of doing this, so I've got the sliders on the notes page. And I can do the horizontal translation, vertical translation. So I've actually got 2 pages over here. So that's the graphing screen and that's the notes page. So I've used this split option. So you can actually have any of these layouts. So I'm using that particular layout, so top and out, so top and bottom. I can have the 2 side layouts there. And lastly, I have got over here is the tan graph, exactly the same thing again. So that's the dilation, that's the horizontal translation, sorry, not the horizontal translation, the period. That's the horizontal translation C. And the vertical translation as well. So you can do that with all the graphs. And that slide is just showing you how to insert sliders. So I won't go through that bit because Roger has already done that. And my intention was to finish exactly at 8, and I have done well to finish at 8. The only thing I did was to kind of rush through everything. But you will actually get my PowerPoint, and you'll also get the calculator file, the TNS file. So you can actually have a play with both. So they are ready to use files. Thank you, and I'll pass it on back to Brian now.
Fantastic. Thank you very much there, Sanjeev. And once again, the sliders are just a natural gem for the transformations, whether it be the graphing of polynomial functions or trigonometric functions. I think everyone could see how beautifully that lends itself to those things. And also the relational graphing for inverse functions. Our topic, of course, was functions, but hey, we've got relational graphing as well, but that can be a neat trick for linking through how to get an inverse function, as you also showed us through the data capture. Data capture, again, is just a wonderful tool. The piecewise functions, once again, a very clever way to illustrate a few things there at once, and a reminder to the viewers that you can access that through the template key on your calculator to set up the piecewise functions, and then of course you have to define the different parts of the domain for each part of the function. Thank you again, Sanjeev.
My pleasure.
In fact, thank you also to Roger. So both our presenters this evening have done a great job and delivered us a wealth of information there. Remember that you do get copies of the files. Sanjeev, I know, as I said, having worked with him a few times, prepares extensive PowerPoints and so you'll be able to work through that at your leisure and share with your students. Just while I go into the closing remarks, now is your opportunity to ask any last-minute questions or just express your gratitude to our presenters. We always appreciate that, and after I close the event, you will be taken to a page where we invite your constructive feedback. Thank you very much. Within a couple of days, you will be getting your certificate of attendance at this training event, and that will also include links to where you can get the files. And on your screen now, the links to where you can watch this again or any of our past webinars, either selecting the on-demand section from our professional development page on the web page, or they're also on YouTube. We found that students in particular like watching these events on YouTube, on our YouTube channel. Please subscribe to the newsletter if you're not doing so already. It's quite possibly how you got news of this event in the first place, but we have many more to come. If you have other questions about the technology, about the activities, the phone numbers are on your screen now. And I will close the event, bidding all a good night, and once again, thank you to our presenters, Roger and Sandy.